Before NASA had landed anything on the Martian surface, a Soviet lander touched down on Mars and started transmitting. And then, 14.5 seconds later, it stopped. The story of how the Soviets got that close and how they lost it is one of the strangest stories that almost nobody outside of Russia tells, because the man who lived it only wrote it down decades later. His name was V.G. Perminov. He was the leading designer for Mars and Venus spacecraft at the Lavochkin Design Bureau, the organization that built almost every Soviet planetary probe after the mid-1960s. He sat in the rooms where these decisions were made. And the document he left behind, translated into English and published by NASA in 1999, is the closest thing the world has to an honest record of what happened. This is the difficult road to Mars. The first Soviet Mars spacecraft was developed in 1959. That is earlier than most people realize. It was begun in the Experimental Design Bureau, known as OKB-1, under the supervision of Sergei Korolev, the same Korolev who had built the R-7 rocket that put Sputnik in orbit and launched Yuri Gagarin. Mars was supposed to be next. The first project was called 1M. It had 3 objectives: investigate interplanetary space between Earth and Mars, study Mars from a flyby trajectory and obtain images of its surface, and check whether onboard instruments could even survive the journey and still talk to Earth from a distance nobody had ever transmitted across before. These were not modest goals. The conditions of interplanetary space were unknown. Everything between Earth and Mars existed in the form of scientific hypotheses, not measurements. In October of 1960, 2 spacecraft of 650 kilograms each were launched. The third stage of each rocket failed. Neither spacecraft reached the proper trajectory. The team learned from it. That is the line Perminov uses. They learned the way small children learn to walk by falling. The next attempt came 2 years later with a multi-purpose spacecraft called 2MV that could explore both Mars and Venus. On November 1st, 1962, a 4-stage Soyuz rocket launched the spacecraft Mars 1, weighing about 893 kilograms, into a Martian trajectory. The solar panels opened, the orientation system locked onto the sun, and then the telemetry started showing something bad. A valve in the orientation system was leaking gas. Slowly, but unmistakably, it would lead to failure. The project managers made a clever choice. They switched the spacecraft to gyroscopic stabilization, which allowed the solar panels to keep facing the sun even with the leak. It bought time. Mars 1 transmitted data on the characteristics of interplanetary space all the way out to a distance of 106 million kilometers from Earth. Then, on March 21st, 1963, the transmitters fell silent. Mars 1 was the first object made by humans to send back real information from deep interplanetary space. It also failed before it ever reached Mars. Both things are true. This is the rhythm of the Soviet Mars program. By the mid-1960s, the political situation had changed. President Kennedy had announced Apollo. Korolev was being pulled in 20 directions at once. He needed to concentrate on the lunar program and the powerful N-1 rocket that was supposed to carry it. So, in April of 1965, he transferred the lunar and planetary spacecraft work to a different organization, the Lavochkin Design Bureau, led by G.N. Babakin. Korolev himself visited the Lavochkin Design Bureau in July of 1965. It was the first and only time he ever set foot there. There is a moment Perminov describes from that visit that is hard to forget. A few months later, on a different project, Korolev died during surgery. The whole Soviet space program would feel that absence for the next 30 years. But the Mars work continued, and it is here that the real anchor of this story shows up. The figure who threads everything together, Babakin. Because for the next 6 years, every decision about Mars went through him. Every impossible deadline. He is the spine of this story, whether he wanted to be or not. The first big project under Babakin's leadership was M69. The launch window for Mars in 1969 was only 20 months away. The team had to review the previous spacecraft, design a new one, build it, test it, and launch it all in less than 2 years. Every detail was a compromise between physics and political pressure. The Soviet Union was competing with the United States, and the leaders of the country were unwilling to concede. Mariner 4 had already transmitted preliminary data from a Mars flyby. The Soviets did not want to repeat what the Americans had already done. They wanted more. The first version of the M69 design used a propulsion system originally developed for lunar spacecraft, with 4 spherical fuel tanks. The Martian lander was attached to the side. It was an awkward configuration that contradicted major instructions from above, but it was the only way to make the 1969 launch window. They began testing the elastic membranes that would push fuel out of the tanks. After a few months of storage, the membranes started failing. Sometimes the seals didn't hold. They could not find a fix in time. Babakin made an unexpected decision. With only 13 months left until launch, he scrapped the existing design and started over with a new spacecraft that used a different engine, with internal supply tanks. The M69 spacecraft eventually passed its tests. The brackets for the orientation micro-engines snapped off during vibration testing, a fatigue problem that took some redesigning. The micro-engines themselves had a sealing problem after a few thousand insertions, which was eventually fixed. 2 M69 spacecraft were sent to the Baikonur launch complex, and then came February of 1969. During the launch operations, the powerful N-1 rocket, the one Korolev had been building for the lunar program, exploded. The blast was enormous. The temperature outside was 30 below 0 Celsius. The central heating froze. They worked on through it. On March 27, 1969, the first M69 spacecraft was launched. The loudspeakers reported normal flight. First stage separated, and then, after a minute, silence. No signal. The third stage of the rocket had exploded. The remains fell into the Altai Mountains. On April 2, 1969, the second M69 spacecraft was launched. A few seconds after liftoff, black smoke appeared from the right engine. Then the whole rocket transformed into a luminous mass of fire. Everything was finished. That is how Perminov describes it. 2 sentences. Everything was finished. The team had built 2 spacecraft from scratch in less than 2 years, and both were destroyed before they ever left Earth's atmosphere. The political pressure on Babakin must have been immense. He chose not to ask the government to postpone the next launch. He decided, instead, to go even bigger. The next opportunity was 1971. It was a year of conjunction, when Earth and Mars were at their minimum distance. That happens only once every 15 to 17 years, which means a heavier spacecraft can be launched with the same amount of fuel. The team made a decision that surprised even foreign observers when it became public. They would not launch 1 Martian probe, they would launch 3. The first spacecraft would carry a heavy load of fuel and instruments and would arrive at Mars first, going into orbit. It would also serve as a radar beacon for the 2 that followed. The second and third spacecraft would each carry a lander. The plan was to put the first artificial satellite around Mars before the United States could do the same with Mariner. This is the project that became M71. It is also the project that, against all expectations, almost worked. The team had to redesign the propulsion module again to hold more fuel. They scrapped the hermetically sealed cylindrical instrument modules from M69 because every time something failed, the whole cable network had to be disconnected to replace it. A young designer named V.A. Asyushkin proposed a new configuration, a central spherical fuel tank, an instrument module attached below with a separable lower cover, so engineers could actually reach the instruments without disassembling the whole craft. solar panels, the high-gain antenna, and the radiators all attached around the central tank. The lander on top. It was a beautiful design. Perminov notes, almost in passing, that this same configuration would later be used not just for Mars but for Venus, for missions to Halley's Comet, and for astrophysical observation in Earth orbit. Once they finally got the geometry right, they kept it for decades. The control system was a different story. Babakin gave it to N. A. Pilyugin's organization, the largest in the Soviet Union for that kind of work. Pilyugin's first proposal was based on the control system for the last stage of the N-1 rocket. The Lavochkin team rejected it unanimously. It was heavier and required more power than the M69 system. Pilyugin offered to develop something better, but he could not finish until 1973. That was unacceptable. The two organizations argued for months. At one meeting, the normally calm Pilyugin suggested, completely seriously, that Babakin fire Demekhin, who was the main opponent of the new system. Eventually, the heads of both organizations went into a side room for half an hour and came out with a joint decision. Pilyugin's system would be installed. The Lavochkin team would, in Perminov's words, growl at Babakin like soldiers growling at a general who lost the battle. Only a year later did they realize how clever the choice had been. The new control system provided the accuracy needed for a soft landing, weighed 167 kilograms, and consumed 800 watts. It made a soft landing possible. The lander itself was the strangest engineering challenge of the whole program. It had to descend through a Martian atmosphere whose actual properties were still mostly unknown. It had to survive the impact of a free fall from low altitude, because the lander was too light to descend with the kind of Doppler radar guidance American probes would use. The team eventually settled on a design with foam plastic packed around the entire automatic Martian station, a thick cushion of foam 200 millimeters thick on the lower part, blanketing the lander like a layer cake. Babakin approved Perminov's idea after looking at the alternatives and rejecting them all. There is a moment Perminov describes from a visit to the institute that built the gunpowder cartridges for the lander. He arrived one morning and saw the wall of the production facility lying on the ground next to the building, while inside the line was still running. He asked his acquaintance whether they were remodeling. "No," his friend said calmly. "Yesterday the gunpowder cartridge exploded. The wall is specifically designed to fall down as a single piece, so the rest of the facility stays intact. Today, they would put it back. People worked at this kind of place because, somehow, they did. The parachute had to be tested at conditions no parachute had ever faced. Low atmospheric pressure, high velocity, speeds above the speed of sound. The team came up with a new method using a meteorological rocket called M100B, which lifted a 1/5 scale model of the lander to an altitude of 130 kilometers. In freefall, the model accelerated to the right speed, and the parachute deployed. They ran 15 of these launches just to check the system under different flight conditions. To plan all of this, Perminov did something nobody at the Lavochkin Design Bureau had done before. He used an American project management technique he had read about in a Soviet newspaper. The article said the technique had been used to develop the Polaris ballistic missile in the United States. He spent more than 15 exhausting days laying out a planning poster 3.5 meters long, filled with events and connections. Babakin approved it in November of 1970. The technical documentation was issued in June of 1971. The skeptics were embarrassed. By May of 1971, 3 spacecraft were ready to launch. Spacecraft M71 went up on May 5, 1971. The Proton rocket and booster block D worked perfectly. The spacecraft was placed in its predetermined Earth orbit. About an hour later, after orbiting Earth and approaching Guinea Bay over Africa, Block D was supposed to start a second time and transfer the spacecraft onto an interplanetary trajectory. A ship in Guinea Bay was watching for it. The engines, did not ignite. A few minutes later, when Block D flew over the Yevpatorizhia control facility in Crimea, the telemetry told them why. No command had been issued to start the engine. An analysis showed that the operator had typed the 8-digit code into the spacecraft's control system in the wrong order, reverse order, a human error, not a technical one. The first spacecraft was lost. The radar beacon they had planned to use to guide the other two to a precise Mars approach was gone. They would not have detailed information about Mars's exact position in space when the landers needed it. That left Mars 2 and Mars 3, launched on May 19th and 21st, 1971. Both made it onto interplanetary trajectories. The first trajectory correction was made in early June. The onboard equipment performed without problems. Communication with the spacecraft was maintained at night. The flight management group settled into routine. And then, on June 25th, the routine broke. "A bright sunny morning," Perminov writes. The telephone on Babakin's dedicated line rang unexpectedly. "Come urgently," his troubled voice said. Babakin was pacing his office when Perminov arrived. "Communication with both Mars failed last night. Get the team together and fly out to Yevpatorizhia immediately." In the middle of vacation season, ordinary commercial flights to Crimea were impossible to book. Perminov called the deputy minister, explained the situation, and got permission to use the ministry's airplane. The ministry's airplanes were parked at a separate airport but had Aeroflot painted on the side, like passenger aircraft. 3 engineers boarded an empty AN 24 inches Moscow and flew to Simferopol. When they landed and walked off the plane, the porters at the terminal rushed up with their carts and then froze. In the middle of the vacation season, an empty airplane had arrived from Moscow, stunned porters struggling to grasp the reality. Perminov compares it to a scene from a Gogol play. The defects on Mars 2 and Mars 3 were exactly identical. The original transmitters in the decimeter band had failed first. The duplicate transmitters had been activated, worked for a while, then failed too. The centimeter band transmitters were activated and were operating, but the signals did not reach Earth. The radiation sensor at the antenna mirror permanently showed nothing. 2 spacecraft, hundreds of millions of kilometers apart, with the same fault. The team worked through 2 consecutive nights. The first night yielded straws of hope. The second night was productive. They identified the operating conditions in which the duplicate transmitters worked, in the decimeter band, without errors. Communication with the original transmitters was re-established, with limited operating time. The signal in the centimeter band still did not reach Earth. The team eventually concluded that the antenna's radiator was overheating, possibly from absorbed solar energy. In future projects, they installed a cloth tent above the antenna mirror, and the design worked perfectly. After 2 days without sleep, Perminov gave Minister Afanasyev the results of their effort. Their actions were approved. Immediately afterward, a communication session began with the Soyuz 11 spacecraft. The voice of cosmonaut Volkov came over the loudspeaker. "It is impossible to eat the steaks." Then, a few minutes later, fire in the spacecraft. The flight manager asked the commander what was happening. "We had a short circuit, but have already fixed it." Volkov is a little excited. "Don't worry, everything will be all right." The next day, the cosmonauts of Soyuz 11 died during their return to Earth. A week later, on July 1st, when Perminov returned to Moscow and tried to resume normal work, news came that Babakin had died of a heart attack. This is where the spine of the story bends. Babakin had carried this program from the moment Korolev handed it to him. 6 years of impossible deadlines, vibration tests that shook walls, gunpowder factories with falling down walls, control system arguments, transistor failures, and somewhere in between all of it, 2 Mars spacecraft were halfway to their destination. The spacecraft would arrive without him. S. Kryukov was appointed the new main designer. He had been the deputy of Korolev. He was, by all accounts, highly qualified. The Babakin-Kryukov team had already been working well together. The flight continued. In November of 1971, a second trajectory correction was made successfully. Both Mars 2 and Mars 3 were closing in on the planet. And then, in the last few weeks before arrival, an unusually strong dust storm covered the entire surface of Mars. Astronomers said they had never recorded a dust storm like it on the Martian surface before. Now, let's come back to Babakin's lost spacecraft for a moment, because here is where everything he had built was about to be tested. The Mars 2 spacecraft arrived first. On November 21st, 1971, the Space Automatic Positioning System was used to make the third correction. The Mars 2 lander was directed at the planet. The orbiter went into a Martian orbit with a pericenter height of 1,350 kilometers and a period of 18 hours. That part worked. But the lander operation did not. After the second correction, the trajectory had been close to predetermined. The onboard computer issued a wrong command to decrease the height of the pericenter of the flyby hyperbola. As a result, the lander entered the Martian atmosphere at too steep an angle and hit the Martian surface before the parachute system was even activated. Perminov is direct about why. They had not had time to fully test the computer programs for the Space Automatic Positioning System. They never got to perform the modeling case where the real and the previously calculated trajectories happened to coincide. If the first Soviet-American data exchange, what Perminov calls the first space barter, had happened a year earlier, in 1970 instead of 72, the team would have had the precise American data on the Martian ephemeris and would have controlled the flight from Earth-based commands. They didn't, so Mars 2 hit the surface. It still mattered. It was the first human-made object to reach the surface of Mars. A third correction to Mars 3 was made on December 2, 1971. The lander separated from the spacecraft and entered its predetermined trajectory. After 4 hours and 35 minutes, the Mars 3 lander entered the Martian atmosphere. It landed at a location with coordinates 45 degrees south and 158 degrees west. The orbiter went into Mars orbit. It transferred to 3-axis stabilization. The cover of the star sensor was opened. Dirt was deposited on the viewport of the sun sensor, and the 3-axis stabilization was lost briefly. After an hour, the cover of the second star sensor was opened, and the spacecraft was transferred back to stable orientation. The transmission of the panoramic images of the Martian surface recorded on the magnetic tape from the lander was initiated. The signal came in. The main engineer of the Radio Institute was standing close to the rack where the signal was displayed. He gave a command to reduce the signal because it was too strong. The telephotometer data started transmitting. There was a gray background with no details. In 14.5 seconds, the signal disappeared. The same thing happened with the second telephotometer. 2 telephotometers, working in independent radio bands, both failed within 1/100th of a second of each other. They could not find an answer to why. Later, Perminov discovered something. During the Second World War, British radio operators in the Lebanese desert had transmitters fail because of coronal discharge during dust storms. On Mars, dust particles are smaller, the humidity is lower, and the atmospheric pressure is much lower than on Earth, but the wind velocity is higher. The leading hypothesis Perminov offers is that a coronal discharge cut off the signal. He doesn't claim it as fact, he just notes the suggestive parallel. Even if the radio link had worked, the dust storm was so thick that the surface was invisible. Both Mars 2 and Mars 3 orbiters kept trying to image the Martian surface, but the dust completely obscured the topography. Even Mount Olympus, with its elevation of 26 kilometers above the average Martian surface, was invisible. During one mapping session, an image of the full Martian disk was obtained, showing a distinct layer of clouds above the dust cover. The orbiters worked for 8 months. They mapped the temperature and pressure on the Martian surface. They measured the soil density, heat conductivity, dielectric permeability, and reflectivity. They discovered heat flow anomalies on the surface. They determined that the temperature of the northern polar cap was lower than -110 degrees Celsius. They obtained altimetry data. They found that the concentration of water vapor in the Martian atmosphere is about 5,000 times less than in Earth's atmosphere. They measured the Martian magnetic field. They discovered the layered structure of the Martian atmosphere and observed its luminosity at a distance of 200 kilometers beyond the Mars terminator. The orbital mission was completed, but what everyone outside the Soviet Union remembered was the lander, 14.5 seconds. A gray frame with no details. In 1973, the team tried again. 4 spacecraft this time. Mars 4 and Mars 5 were launched on June 21st and 25th of 1973. Mars 6 and Mars 7 followed on August 5th and 9th. The world headlines called it the Russian Armada moving toward the Red Planet. Scientists thought the Soviets were making a powerful thrust to solve the major Martian problems before the American Viking lander arrived in 1975. The real reason was more political than scientific. The team knew that the launch conditions in 1973 were poor and that one rocket could not carry both an orbiter and a lander, so they launched 2 orbiters and 2 landers separately. The 73 campaign was wrecked by transistors, specifically by a transistor called the 2T312 fabricated at the Voronezhsky plant. Every onboard system used them. Some smart person, as Perminov puts it dryly, had decided to save gold resources by replacing the gold leads inside the transistor with aluminum ones. The necessary tests had not been done. 2 years later, intercrystalline corrosion at the lead area started destroying the transistors. The failure rate began to rise about 1.5 to 2 years after production. For the spacecraft about to be launched, that corresponded to the moment they would arrive at Mars. Replacing all the transistors would have taken 6 months. That was exactly the time remaining. They estimated the probability of completing the flight program at 0.50%. The ministry decided to launch anyway. Mars 4 reached Mars, but its braking system failed, so it could not enter orbit. It made images on a flyby and continued past the planet. Mars 5 entered Martian orbit successfully, but according to subsequent analysis, it transmitted only about 60 images before a loss of pressurization in the transmitter housing ended the mission. Mars 6 lost telemetry from the spacecraft after 2 months, almost certainly the 2T312 transistor failing, but the lander, in autonomous mode, made it to Mars and transmitted information from the Martian atmosphere during parachute descent. The signal from the surface was supposed to relay through the Mars 5 spacecraft, but it never reached its destination. The Mars 6 craft landed in the vicinity of the Valley Samara, perhaps on a steep hill. Mars 7 lost its lander to the same transistor failure. The lander was not put on an encounter trajectory and missed the planet by 1,300 kilometers. 4 spacecraft launched. 1 orbiter completed at least part of its mission. 1 lander reached the surface and went silent. The other 2 effectively missed. After this, Minister Afanasyev called a meeting and asked the Minister of the Electronic Industry one question: how do we avoid numerous failures during the next flights? They got 2 answers. Use 10-year-old electronic components fabricated under well-developed technology, or develop a special program to choose advanced components more carefully. They took the second option. The new components got the abbreviation MB. Reliability went up. Cost went up too, almost 10 times. As they say, Perminov writes, the goal is worth the effort. After 73, the Soviet Mars program never recovered the same momentum. The team spent years working on increasingly elaborate sample return projects, Project 5 nanometers, Project 4 nanometers, Project 5M. The plans grew more ambitious as the politics around them grew more strained. Project 5 nanometers would have required an N1 rocket, the launch vehicle that had blown up at Baikonur during the M69 campaign, and the N1 program was eventually cancelled. Project 5, M, required 3 Proton launches and 3 automatic dockings in space to deliver a sample return capsule. Biologists worried about Martian microbes propagating on Earth if a parachute failed. Academician Vinogradov suggested thermal sterilization of the soil samples while still in Martian orbit, which solved the biological security problem completely. The technical assignment was developed. The preliminary design was approved in January of 1976. In 1978, the Head Institute issued a statement noting the project's complexity, high cost, and low probability of success. Minister Afanasyev decided to discontinue the project for Martian soil return. Perminov writes that the decision seriously damaged the prestige of the Lavochkin Design Bureau. Many organizations had concentrated their specialists on the project, and all of a sudden, they were out of business. Kryukov, the main designer, resigned, saying he was guilty of mismanaging the project. V.M. Kovtunenko was appointed in his place. He had spent the previous 10 years working on intercosmos satellites in Earth orbit, a different category of problem entirely. He decided to find his own way in the new field. He was fascinated by the idea of a multi-purpose spacecraft to study the Moon, Venus, and Mars all at once, called UMVL, Universal Mars, Venus, Luna. The pace was slow. The Phobos 1 and Phobos 2 spacecraft were eventually launched in July of 1988, Phobos 1 on the 7th, Phobos 2 on the 12th. They were the heaviest interplanetary spacecraft ever launched at the time. The flight program was ambitious. Place both spacecraft in Martian orbit, approach the Moon Phobos, land 2 automatic stations on its surface, conduct a remote study of Phobos soil chemistry, conduct an extensive study of Mars from orbit. Neither spacecraft completed the full mission. Phobos 1 was lost on the way to Mars in August of 1988. The cause is one of the most painful single-point failures in the history of spaceflight. A technician at the Yevpatoria ground station, the same control facility that had been involved in every Soviet Mars mission since the M71 launches, sent up a command sequence with a single missing character, a hyphen left out of a keyed command. All commands were supposed to be proofread by a computer before transmission, but that computer was malfunctioning. The technician violated procedure and transmitted the command anyway. The minor alteration in code activated a routine that had been left in the spacecraft's PROM-coded software from ground testing. That routine deactivated the attitude thrusters. With its attitude thrusters off, the spacecraft lost its lock on the Sunday. The solar arrays could no longer be oriented properly. The batteries depleted. The probe died. A single missing character. A spacecraft larger than anything that had ever flown to interplanetary space. Phobos 2 made it. It entered Martian orbit on January 29, 1989, and started returning data on the Sun, the interplanetary medium, Mars, and Phobos. It successfully carried out 3 preliminary encounters with Phobos and returned 37 photos covering most of the Moon's surface. Then, shortly before the final phase of the mission, the part where the spacecraft was supposed to approach within 50 meters of Phobos and release a hopper and a stationary platform contact was lost. The cause was determined to be a malfunction of the onboard computer. 2 of its 3 computers had already failed during the cruise. The spacecraft needed 2 computers to agree on any decision. With 2 of them dead or dying, the third could not outvote them. The Mars 96 spacecraft, launched in November of 1996 with an orbiter, 4 landers, and 22 scientific instruments, failed because of onboard computer and upper stage booster malfunctions. It was never injected into an interplanetary trajectory. It is the last spacecraft Perminov reports. So what did the Soviets accomplish on Mars? Honestly, there is a list, and the list is real. They were the first to reach the Martian surface, even by crash. They were the first to soft land a spacecraft on Mars and transmit anything back, even if it was only 14.5 seconds of gray. They mapped temperature, pressure, soil properties, water vapor, magnetic field, atmospheric structure. They proved that a soft landing on Mars was scientifically and technically possible, but there are things we still don't know. We don't know what was actually in those 14.5 seconds of gray transmission from Mars 3. We don't know whether a coronal discharge in the dust storm killed the signal, or whether something inside the lander failed at the same instant in 2 independent radio bands in a way that has no obvious physical explanation. We don't know what would have happened if the operator at Yevpatoria in May of 1971 had typed those 8 digits in the right order, and the Soviets had reached Mars first. We don't know how the program would have looked without Babakin's heart attack in July of '71. We don't know what a single missing hyphen cost the Soviet space program in 1988. What we do know is that Perminov's book exists. A man who sat in those rooms, who watched the rockets explode and the membranes leak and the transistors corrode, who lost his closest collaborators and kept building, eventually sat down and wrote it all out. NASA published the English translation in 1999. The book is dry. The book is honest. The book is full of the kind of small, exhausted humor that only comes from people who have failed many times in public. The Russian proverb keeps appearing in its pages. A good master does good work. Another, near the end. One beaten person is worth 2 unbeaten ones. There is a photograph somewhere in an archive of the Mars 3 lander, the foam plastic shell wrapped around its automatic station, sitting on Martian soil at 45 degrees south, 158 degrees west. The petals open, the antennas extended. The Prop M instrument, the small device on its 15-meter cable sitting nearby, frozen in the act of measuring soil properties it never got to measure. It has been there for over 50 years. The dust storm that killed its transmission ended decades ago. The lander has not moved. It is still the first spacecraft to softly touch the surface of Mars.